first speaker this evening is Daniel Trewartha from the Faculty of Science, and his topic is the influence of nothing on something.
Where does mass come from? I'm not talking about letting yourself go over winter. I mean at the level of individual atoms. Everything we see around us is made up of tiny particles called atoms. Most of the mass of these atoms is concentrated in their core, the nucleus, which is made up of protons and neutrons. Since the 1970s, we've known that the protons and neutrons themselves are each made up of three smaller particles, the quarks. But if you just add up the mass of the three quarks in a proton, you get a number that's only about 1% of its total mass. If the quarks can only explain 1% of mass, where does the other 99% come from? The answer lies in what's around when there's nothing around. Empty space is far from empty. I've included a picture of empty space on my slide here, and you can see there's a lot more in it than you might have thought. It's filled with this rich quantum sea, made up of particles called gluons. These gluons surround the quarks, forming the complex shapes and structures you can see on my slide, which are constantly popping in and out of existence. They're called gluons because they're what glue the quarks together into protons and neutrons. But they have other strange effects on the quarks. Using supercomputer simulations, we know that even though the gluons themselves don't have any mass, it's something about the way that the gluons interact with the quarks that produces almost all of the mass we see around us. It's a process known as dynamical mass generation, and without it, we'd all weigh about as much as a mobile phone. But we don't yet fully understand the behavior of the gluon sea. We know that it can produce the mass we see around us, but we don't know how it does this. What is it about the way quarks and gluons interact that creates mass? What's the simplest underlying aspect of the gluon's behavior that is responsible? That's where I come in. I've shown it's the ability of the gluons to form a special arrangement called a center vortex, which is the key. The center vortices are tiny structures hidden within the chaotic, fluctuating background of the gluon sea, but they play a vital role. Using supercomputer simulations, I've taken snapshots of the gluon sea, just like the one on my slide, and carefully picked out the center vortices hidden inside. Once I've removed the center vortices, what we have left looks almost exactly the same as it did before, but it doesn't perform in anything like the same way, much like the Australian cricket team. Instead of being glued together into protons and neutrons, the quarks bounce around freely like tiny billiard balls, and the only mass we see is the mass of the quarks themselves. Using center vortices, we can explain where mass comes from and why, when there's nothing around, there's a lot more around than you might expect.